Hello again. My name is Vickenty and I write Perl code at booking.com. And if you haven't heard enough, we're hiring. If you want to work at Booking, please visit this website. It has everything you may need to know. If you have any questions, come grab one of us, me, Gonzo, Sawyer, John, maybe someone else. And I will talk about writing Perl extensions in Rust. So Perl interpreter is written in C, and naturally it is the language of choice for writing Perl extensions. C is a powerful language, but it is a sharp tool and must be used with care. It is very easy to do something wrong and take down the whole interpreter with you. For example, where Perl has runtime checks to protect you from coding errors, C just assumes you've done the right thing and carries on. To give you a concrete example, when you dereference a value in Perl, Perl checks that it is defined and generates a runtime error if it isn't. C compiler just assumes, oh, it will be okay when program runs and just dereferences it. A lot of functions in excess return null pointers, and it is not a valid thing to read or write from a null pointer, either directly or indirectly, as in this case. It may crash or may not crash and do something else instead, and you must be very diligent and check all return values for nulls before using them. C doesn't have reference counting like Perl does, so programmers must track lifetime of every value they are using, and there is really no way to check for this. It's only to be careful during development. C developers must track size of every piece of memory they are using, because writing past the end of the array is not a valid thing to do and just as bad as reading a null or writing to a freed memory. And there is much more. Just a list of these rules C compiler may assume to be upheld at all times takes 15 pages in the language standard. It's really a lot. And I'm not saying this is because... just wait a second. And Perl Access API doesn't make it any easier. For example, what does this function do?
It returns the index of the last element.
Why does it call len? Okay. C doesn't have reference counting or support for automatic reference counting. Perl does, so similar looking pointers may require different treatment in different situations because Perl doesn't always count pointers as references to be faster. Perl has exceptions while C does not. So if you have any resources held by stack local variables in C, like open files, allocated memory, or something else, you have to protect them from Perl exceptions because then you will leak them if exception happens. Okay, this is like, it's all documented probably, so you can read it and do the right thing by being careful. But last year, Brian Strostrup published a paper where he analyzes the same problems they encounter in C++, and the conclusion he comes to is being careful is not enough. We have to do something else. Rust is a new language that is basically built around the idea that being careful is not enough. It is a compiled, statically typed language with a strong focus on memory-safe programming, not doing the wrong thing with a pointer. It is compatible with C, so it can call C functions, and C functions can call Rust functions, and then it means by necessity that Rust can do everything that C can. It can cast pointers between different types, it can cast integers to pointers and back, it can read and write arbitrary memory locations unrestricted. What is different is that it is only allowed inside spatial unsafe code blocks, which have spatial syntax for them. In C, pointers are very widespread, and you would imagine that unsafe code blocks would be everywhere in Rust. So a lot of Rust language features are actually dedicated to either making not necessary to write unsafe code blocks or isolating them behind some kind of safe abstraction. For example, when you have an array, it will be represented as a safe Rust type, which does all the checks, but inside, and it is documented and guaranteed, it will be contiguous array of memory with a pointer and works pretty much just like a pointer in C. And this is not really a new idea, Perl itself can be viewed as a safe abstraction around unsafe C code, where it has just different set of trade-offs. You can never write Perl code that reads uninitialized memory or crashes the interpreter. You shouldn't be able to. And this is what I was thinking. Can we use Rust safety features to write Perl extensions in a way that abstracts away unsafe details of the Perl API, abstracts away unsafe things that you have to deal with in C, while still having benefit of using a compiled language? And let's see how it turned out. We'll write a small subroutine that goes over the Perl array and adds up elements, makes a sum of array, and returns it back to Perl. We'll start with a basic skeleton of a module. Things with an exclamation mark at the end are Rust macros. They are used. Access macro you see here is used to set up the module structure in a way that Perl can understand. And access return macro just takes the values and returns them back to Perl. Sum array takes one argument, context, which represents the Perl interpreter and the whole argument stack it contains within. We use contexts to communicate with Perl. Then we pull the first our only argument from the stack. So in this module, I tried to keep the names used by access the same. So scalar values are still called SVs, array values are still called AVs, and so on. And stack operations have ST prefix. What's different that there are no pointers here, where Perl gives you a pointer to stack to an SV in C. Here, pointer is hidden inside the Rust type called SV, and it has only operations that are valid for SVs, so you cannot put it into the wrong position. So we are summing array. Arrays are passed as references, so we need to dereference it first. But what if param is not a reference? What will happen? In C, you just required by documentation to check at all times that you're dealing with a reference. But if you will make a deref AV function in C, it could return a null pointer. In Rust, there is a special type for handling situations when there may be something does not exist. Something is not defined, something is missing. It's called option, and deref AV returns an option if the param is not. So it returns option at all times, but option will be undefined if the param is not an array reference. This code does not compile because I'm not checking. It gives me an error because deref AV returns an option. I need to check. Option has a lot of methods. One of them is expect, which checks that value is there and returns it. Otherwise, it creates a runtime exception with the provided message. So it is similar to or die idiom in Perl, quite common. Then we set up our accumulator variable and the loop. Rust can infer types for most local variables, so type annotations are not really required. And in this case, sum and index has no explicit types, but they will have concrete types when program runs. Then we pull items from the array one by one and add them to the accumulator. Again, in C, AV fetch may return a null pointer if you have a gap in the array or the element is not defined. Here, we return an option again, and in this case, I'm just checking explicitly using the language syntax that whatever is returned is sum, which is the term for having a value, and inside sum will be our item that we're looking for. Perl arrays contain SVs, but we are adding item to the floating point variable. Array fetch can convert from SVs to basic Rust types on the fly when you fetch elements from the array. Because of the safety goals I was mentioning earlier, every stack local variable in Rust is reference counted, which usually does not happen in excess code. To avoid doing reference count increment and decrement every time we fetch an element of the array, we convert it as soon as possible, where no user code can run in between, and we can safely omit this increment and decrement hurdle at compilation time. So when the loop finishes, we return the sum. It is converted back to NSV and returned to Perl. This is not bad. It's 15 lines of code to go over the array, but we can do better. Let's rewind a bit and try again. Rust standard library also has iterators, which is a standard type. You can implement it for any kind of type, and then you have about 50 different utility methods you can use on them. So first of all, it is implemented for Perl arrays as well, so we can get an iterator using iter method. One of the useful methods provided by the iterator in the standard library is map, which gets a code block which replaces undefined values in the array with zeros, so we can safely add them up. They all will be present and defined. Now, inside the code block, you see unwrap or. Like I said, elements of the array may be missing or undefined, so we need to do something about it. We have option, so code block gets an option again, and unwrap or is a method of option that either returns the value inside the option or the default value provided to it. So it is it is a Rust analog to common Perl / operator. Another method is sum, and we're done. This is a little bit better, I think.
What happens if one of the elements is not a number?
So we call a Perl API function that takes an SV, it returns a number, and the way it is written, it will emit a warning and return 0 or whatever it interpreted the string or what reference as. So if you put a reference inside the array, it will still return the address. But that's how Perl works, and that's what would happen in pure Perl code as well. This talk wouldn't be complete without benchmarks, of course. I tried both versions of the program you just saw, pure Perl implementation of it on top and pure excess C implementation at the bottom. Rust version runs about 3 times faster than pure Perl, and excess is about 5 times faster than Rust. Rust should have performance similar to C because it is a compiled language and its performance is one of their important goals. So what is going on? It turns out that most of it is my fault because of how I treat Perl API. First is reference counting. It's not a big drawback in this case because we only do it twice per subroutine call, but it still adds up a little bit overhead to the excess version. Second is there is no hot path inlining. Perl excess API uses C macros to inline hot code paths into this compiled subroutine directly, so you have very efficient code. Rust cannot use C macros, so I decided to treat Perl API as a black box instead of re-implementing them, so I do a function call every time I need something from Perl. This adds surprising amount of slowdown. And the third one is exception handling, because both Perl and Rust has exception handling, and because we have reference counted variables in the stack, we need to clean them up if the exception happens. So consider this example where we have Perl code calling into the Rust subroutine, and Rust subroutine is calling into excess code. When Rust subroutine finishes, Rust compiler will call destructors, thing that does the cleans up after the user. So it will free any allocated memory if needed, and it is also used to decrement reference counting when variables leave scope. Now imagine excess code dies. It will jump straight through all of this into the closest eval block. And this is not what we want. It leaks all our local stack variables, all the open files, all the allocated memory. So I had to insert 2 guard blocks on each side of Rust code. guard on the right catches Perl exceptions, converts them into Rust exceptions, which then correctly propagate through the stack, doing all the cleanups as necessary, and then guard on the left catches Rust exceptions and converts them into Perl. In case of a Perl exception, it will resume unwinding in Perl. And this is very slow, because I have to do it for every single little thing I do. To summarize, it is definitely possible to write an access module in Rust. It is safe as planned. We have no pointers, we have no chance of having a dangling pointer, we have no null whatsoever to worry about. And of course it is slower, but that was expected because Perl is very optimized and we're not really working close enough with the API. I would like to thank a lot of people, first Booking.com for letting me present here, people of the P5P club we have at work where people hack around with Perl internals and access, and people at the Rust RC channel where they answer all my stupid questions all the time, and the Rust community in general. And that's it. Code is on GitHub. If you want to look closer or play with it, by all means do. If you open an issue, I'll be more than happy. If you have a pull request, I will be ecstatic. Questions? Yes?
So do you have a plan for tackling the slowness?
The question is, do I have a plan for tackling the slowness? I have some vague ideas. The first implementation of this module was even slower than Perl, so I think this result is already quite good. I don't think much can be done in improving this situation right now, save from investing massive amount of time in re-implementing parts of the XS API in Rust, and then you have the problem that it is only stable in the name, because the names of things you call stay the same, but their implementation changes all the time, so it will have to track released Perl versions very closely. And the slowness is really only in the interaction with Perl, because the examples I showed mostly do only interacting with Perl. So if you have any heavy computation, if you use Rust libraries, if you use Rust strings or vectors, then it will work much faster and you will only incur this overhead when you talk to Perl API, you use Perl values. Yes?
So in your benchmark, did you call some array several times, or did you call it with a big array? Because from what you're saying, it seems if you call it with a very big array, but a few times, it will be comparable to access, right?
No. I called it many times and with a big array. So because I didn't want to measure overhead of doing an access call, but more to see how much time is wasted in doing the computation. The problem with slowness is that when you have stack fetch, for example, to get an argument, I have to create exception context for Perl in like an eval block and put fetch there. Maybe it is not necessary, but it is not quite documented, and I decided to safely wrap everything for the first version. And then when you have an array fetch, also I create a new exception context, trap exception, and do all the dance again. So it's not one-time cost, it is per call cost. Yes? So to install such a module, they would need a Rust compiler installed, of course, and there are a couple of Perl modules that one is doing the glue between Perl access and whatever you may want to use. It wraps Perl macros, but that will be installed automatically. And the second one will be required at the glue between Perl build system and the Rust build system. But these, I think, should be handled by either automatically or the dependencies of your cpan modules. So, and Rust build system also has built-in dependency management, so any dependencies from Rust side that you may want to use, they will be pulled automatically as part of the build process. please.
What if you introduced an exception check for the entire sub instead of for each function in the sub, basically reducing the amount of guards that you have?
I can check at the top level, but then I don't know where the exception happened, so I cannot propagate it through the call stack and do the right cleanups. Any other questions?
The example currently on screen, which bits it actually invokes SVNV? Is it in the addition operator, some classic Python?
No, SVNV is executed as part of the fetch.
Okay. How does the type influencer, I guess, know that you wanted NV rather than...
It's actually quite funny how it works. So when I declare sum, I assign a floating point value. So Rust knows it's one of the two floating point values supported by the compiler. When I do fetch, it can see that of all the types as a fetch can convert an SV to, there is one floating point value, so it picks that one. If there were any ambiguity, it would just fail to compile and say, please add some type annotation somewhere so I can tell what is going on. Then I guess we're done. Thank you very much.